Educators often operate on a straightforward assumption. If you link an abstract scientific concept to a familiar local phenomenon, students will automatically understand it better. This is the driving premise of contextual teaching and learning, or CTL. It's an instructional approach designed to pull students out of rote memorization by grounding academic content in their everyday reality. The broad consensus in educational research is that making science real pushes students toward higher-order thinking skills. They stop memorizing terms and start analyzing systems. The theory backing this up is Vygotskian constructivism, which argues that a student's social and cultural context is the primary mediator for building new knowledge. Because of this theoretical foundation, curriculum designers frequently treat the mere inclusion of local context as a flawless instructional bridge. If the example is local, the learning is assumed to be guaranteed. To test how this actually plays out in a physical classroom, researchers conducted a case study at SMPIT Ashifa boarding school in Subang, Indonesia. Subang offers a dense concentration of relevant ecological phenomena. The area features geothermal springs, extensive tea plantations, and robust local agriculture, giving the science teachers a wealth of raw material to draw from. These local examples look perfect on a lesson plan, but assuming their presence automatically generates scientific understanding masks a severe cognitive trap. The Ashifa study revealed a distinct anomaly in the data. While 4 out of the 5 observed students experienced deep comprehension through the contextualized lessons, one student had the exact opposite reaction. For this student, the highly relatable local example failed to clarify the science. In fact, it actively sabotaged their learning process. The high-performing students found that seeing fermentation bubbles in a jar or plants leaning toward windows confirmed exactly what the textbook had only described in text. The struggling student, however, reported a paralyzing confusion and a doubled mental workload. This single data point highlights a mechanical failure in the classroom. Highly relatable, localized examples can break a student's cognitive processing if the semantic bridge connecting the example to the science is flawed. Researchers analyzed a biology lesson on fermentation. To anchor the abstract biological process, the teacher utilized local pineapple waste as the physical context. Student 1, classified as scaffolding adaptive, easily linked familiar local processes, like the making of fermented cassava, known as tape singkong, directly to the scientific term. Student 5, classified as scaffolding resistant, failed to make that same connection. Looking at this split-screen cognitive processing map, we can see exactly what Student 5 meant in their qualitative feedback when they stated, "It feels like 2 tasks at once." Instead of acting as a translator, the local context became an additional burden. The student was forced to process the familiar local example and the abstract scientific terminology as 2 entirely separate variables. Trying to hold both of those unlinked variables in their head simultaneously caused their working memory capacity to be exceeded. Educational psychologists refer to this as the split attention effect. When local context is presented without a clear structural schema to tie it to the academic concept, it acts as an obstacle rather than a bridge. We can diagnose exactly why Student 5 failed using Sweller's cognitive load theory. This indicates a structural design failure in the lesson itself, rather than a lack of student intelligence. To understand the failure, we have to differentiate between the 2 specific types of cognitive load activated when context is introduced in the classroom. This schematic of human working memory illustrates the first type, germane load. Student 1 used the local context as a productive, load-bearing structure to help them mentally assimilate the new scientific term. The second is extraneous load. Student 5 experienced the local context as irrelevant noise. Because the link wasn't explicit, the extra information crushed their working memory capacity, causing the mental foundation to crumble. Contextual teaching and learning inherently carries the risk of extraneous overload. It requires the instructor to explicitly manage exactly how the student's folk knowledge connects to the Western science. This shifts the focus away from the student's psychology and directly onto the instructor's real-time pedagogical content knowledge. We have to look at how the teacher actually attempted to resolve this extraneous overload while the class was in session. The researchers discovered that the teacher relied on an undocumented, spontaneous 5-step bridging procedure to save the lesson. Step 1, the teacher visually detects confusion, scanning the room for nonverbal cues like blank stares or signs of split attention. Step 2, the teacher actively interrupts the formal flow of their own lecture. Step 3, they deploy a folk knowledge prompt, asking the room about a highly familiar household process, like watching dough rise. Step 4, the teacher pauses and waits for an affirmative student response. As mapped out in this flowchart, Step 5 is where the teacher seamlessly attaches the rigid scientific terminology directly to that newly activated folk schema. This specific sequence triggered an emergent, highly analytical debate among the students regarding the efficiency of different fertilizers. The physical presence of pineapples in the room didn't guarantee comprehension. The lesson succeeded entirely because of the teacher's real-time semantic engineering. But the researchers identified a critical systemic failure surrounding this exact interaction: the documented practice gap. That highly effective 5-step semantic bridge exists absolutely nowhere in the school's formal lesson plans or teaching modules. This is an example of craft knowledge, expertise that lives entirely within the individual teacher's intuition. If that specific teacher leaves the room, the strategy vanishes with them. Leaving this critical translation step out of the institutional documentation creates a severe vulnerability. It guarantees that introverted students who don't visibly show their confusion, like Student 5, will inevitably slip through the cracks. Curriculum designers and instructional psychologists have a proposed systemic solution to this vulnerability. Localized pedagogy must be extracted from the teacher's head and explicitly codified into the curriculum architecture. Curriculum designers recommend implementing a bilingual visual glossary. Column 1 holds the scientific term, Column 2 holds the local equivalent, and Column 3 provides the bridging definition. Applying the ESIFA case data, you place the scientific term fermentation in Column 1, the local process tape singkang in Column 2, and the specific chemical definition in Column 3. By integrating this directly into the lesson plan, the school codifies the teacher's craft knowledge into permanent institutional knowledge. This tool provides explicit scaffolding that preemptively neutralizes the split attention effect before the student ever experiences cognitive overload. Effective contextual teaching requires instructors to treat the link between culture and science as a formal engineering problem. Closing this gap requires more than an observant teacher. It requires a lesson architecture that accounts for the split attention effect before